fluid of Prandtl number 1 at 500 Kelvin flows over a flat plate of 1.5 meter length maintained at 300 Kelvin. The velocity of the fluid is 10 meter per second. Assuming kinematic viscosity is 30 into 10 to the power of minus 6 meter square per second, the thermal boundary layer thickness at 0.5 meter from the leading edge is Prandtl number can be defined as the ratio of momentum diffusivity to thermal diffusivity, which can be written as mu by rho divided by K by Cp into rho, which is equal to mu Cp by K. Right. K is the thermal conductivity of the fluid and Cp is the heat capacity of the fluid. Now for boundary layer problems, for a flow over a flat plate, we have the hydrodynamic boundary layer and the thermal boundary layer thickness and the thermal boundary layer. Delta T is called the thermal boundary layer thickness and delta is the hydrodynamic boundary layer thickness. And these two are clubbed by Prandtl number and given by the relation delta upon delta T, the ratio of hydrodynamic boundary layer thickness to the thermal boundary layer thickness is equal to the cube root of Prandtl number. Now in the problem, it is given that Prandtl number is equal to 1. So PR is equal to 1. That means the hydrodynamic boundary layer thickness is equal to the thermal boundary layer thickness. Let this be question number 1. Therefore, if we can find the hydrodynamic boundary layer thickness, that will be equal to the thermal boundary layer thickness, which we need to find in this problem. Now the total length of the flat plate is given 1.5 meter. And we need to calculate the thermal boundary layer thickness at 0.5 meter. So let's say X from here, from the leading edge. This is the leading edge of the flat plate. So from here, let's suppose at this point, let this be X is equal to 0.5 meter. So at this location, we need to find delta T. Okay, so let X is equal to 0.5 meter. Now, since there is no velocity profile given in the problem, so we will assume Blasius equation for the solution of hydrodynamic boundary layer thickness, which is given by delta is equal to 5 times of X divided by square root of Reynolds number at the location X. Okay. Now to calculate Reynolds number at X, let's write here. So let's write first, this is the Blasius solution. Now to find the Reynolds number at the location X, we know Reynolds number is equal to density multiplied by velocity at X into X divided by the coefficient of dynamic viscosity, which we can also write as Vx into X divided by the kinematic viscosity. Let's substitute the value here. So velocity at 0.5 meter is 10 meter per second into 0.5 divided by the kinematic viscosity, that is 30 into 10 to the power of minus 6 meters square per second. So this will come out to be 1.66 into 10 to the power of 5. Since the Reynolds number at X is equal to 1.66 10 into 10 to the power of 5, which is lesser than 5 into 10 to the power of 5, which is the critical Reynolds number. Okay, so beyond which the flow is turbulent or in the transition condition. So before which the flow is said to be laminar. So this is an example of laminar flow. Okay, so we need to find the hydrodynamic thickness in the laminar region. Okay, as we have already established here itself, but we haven't exactly said the term. This is hydrodynamic boundary layer thickness in the laminar region. Okay, therefore let's write here thermal boundary layer thickness will be equal to the hydrodynamic boundary layer thickness, which is equal to 5 times of X, which is 0.5 divided by square root of the Reynolds number at the location 0.5 meter, which is 1.66 into 10 to the power of 5. Since we need to find the value in millimeter, so we will multiply it by 1000. Okay, so from here we'll get delta T, which is equal to delta is equal to 6.12 millimeter. Okay, therefore the thermal boundary layer thickness, which is also equal to the hydrodynamic boundary layer thickness, because the Prandtl number is equal to 1, is 6.12 millimeter. For more information, you can refer to the NPTEL course, lecture 19, Dimensionless Numbers on Fluid Dynamics for Astrophysics by Professor P. Subramania of the Department of Physics at ISAR Pune.